Hi everyone. So today we're going to be solving a problem that involves some kind of amusement park ride that has a passenger car starting really high up at point A, falls straight down, drops through a path that undergoes centripetal motion from B to C, and then just linear motion from C to D. So the two components to this question, we're going to calculate the normal force at point C, and then we're going to determine how much braking force is needed to stop the car safely at point D. So let's have a look at point C. I'm just going to draw a free body diagram for the cart. This is for the cart at point C. So it'll have a normal force. It has its gravitational force. It's going to do some of our forces in the y, because we're only worried about the y direction. It'll be MAY, Fn minus Fg. And in this case, our acceleration, because it's centripetal motion, is going to be mv squared over r, our centripetal acceleration, which is the v squared over r. So clearly the next step here is that we don't know what the velocity is, but we can determine the velocity. If we have a look here, our car is starting at the top with the initial velocity of just 0. It starts from a stationary position. Then it drops down to point C, where all the energy is kinetic. At the top here, all energy is potential. So let's go back down. We can say our energy at point A is equal to the energy at point C. This is just conservation of energy. Initial energy equals final energy, but I'm considering point A up here to be our final position, or our initial position, sorry, and point C to be our final position. So then I can say, because I know initially it's all potential, mgh at the top equals 1/2 mv squared at the bottom. I can cancel out the masses, and then I rearrange to get 2gh equal v squared. So the square root 2gh equals v. And if I do this calculation, then I'm going to plug in to 9.81. Our height, if we go back up here, this distance is 10 from A to B, and then from B to C, it's 5 meters. So it'll be 15 meters. So if we do this calculation, we're going to get that our speed is 7.16 meters per second. Also note, I didn't put in the units here, but our units on gravity are, of course, meters per second squared. So this is our speed. And now, remember, we're looking for the normal force at point C. So let's go back here. Now we have a velocity that we can plug into that. Let's just do some rearranging first to make sure that we're solving for the normal force. So I'll just rewrite this down here. We rearrange. For the normal force, it's mv squared over r plus fg equals fn. And, of course, fg is just mg. So now, let's plug in some numbers. The mass of our cart was 300 kilograms. Our velocity is the 17.16. That's squared. And our radius, if we have a look here, this portion of the trajectory is our portion that is undergoing centripetal motion, and you can see that the radius here is 5 meters. So that's the value that we put in for our radius, 5 meters. And then we can just calculate mg, 300 times 9.81. I'll put in the units this time, meters per second squared. And don't forget that this velocity should be written like that, squared. So if we plug in all these numbers, it should come out to 20.6 times 10 to the 3 newtons. You can also write that as 20.6 kilonewtons. Okay, so I've just cleared our work. I put our final answer for part 1 up here. That's the normal force at point C, 20.6 kilonewtons. And I've also written down what that velocity is at point C that we calculated, because we're going to need that for part 2. But now we can go on to the second part, determining how much braking force is required to stop the car safely at point D. There are 2 ways that you can solve this. We can either use the work energy theorem, or we could stick to kinematics and Newton's laws. Let's first do it using the work energy theorem. So just a note, that the work energy theorem is the work done on the system is equal to the change in the kinetic energy of the system. So this is really important. This is going to help us because we know that we are starting with this velocity and the cart is coming to a stop. So our final velocity, I'll say VF, is just going to be 0. And this V is really our V initial. So let's just add a few more things in here. Let's actually write out what the change in kinetic energy is from point C to point D. So it'll be EK final minus EK initial. It's going to be equal to the work done. Let's just leave it for there now. I'll specify this a little bit more clearly. This is really 1/2 mv squared final minus 1/2 mv squared initial. It's equal to the work done by the system. Now, if we go back up here, we're given the coefficient of friction here. So we know that from point C to point D, we have a frictional force, and we also have a braking force. That's what we're trying to figure out. So let's split this up even more. We'll specify what the work being done is. So we know that we have the work done by friction and the work done by braking. But these are actually going to be negative values. So I'll just write these in. Work done by, I'll say brake. So if we have a look back up here, we know that we have a frictional force. We're given a coefficient of friction, 0.62. And then we want to know how much work or how much braking force is required to stop the car safely. So we can really split up the work into the work done by friction and the work done by the braking force. I'll call that WF and W brake. Now let's just continue adding things in here. We know that our V final is 0, so I'm just going to cross this out and say V final is 0, so this whole thing is going to be equal to 0. Just going to rewrite our negative 1/2 mv initial squared. We need that, absolutely. Now the work done by friction is going to be negative mu F Fn times the distance over which that force acts. Okay, so this is common, that your frictional force is equal to mu F, coefficient of friction, times your normal force. This is standard, something you'll see in many problems. But when we're talking about work, we know that the work is negative because it's removing energy from the system. In other words, you have less kinetic energy at point D than you do at point C. So it's doing negative work. And we still don't know what's happening with the braking force, so I'll just leave it at that. So we can actually rearrange this and solve for the work done by the brakes. Just going to move over the work done by friction. And the one thing that we don't have is the normal force. Now we did calculate a normal force in part 1, but that is not going to be the normal force for part 2 because we are no longer undergoing centripetal motion. We are for points B to C, but not from C to D. So let's just do another free body diagram here. We of course have our normal force, Fg. If we sum the forces in the y, there is no y acceleration, so that's just equal to 0. And if we add them up, we have Fn minus Fg. So Fn equals Fg. You can also say Fn equals mg. So we can put this in. And now I think we have everything that we need. We can actually plug in some numbers. remember that velocity is the 17.16 meters per second. Remember that mu f is 0.62. And the distance is 15 meters from C to D. So we can plug that in. So if we plug in all these numbers, then we get negative 16.799 times 10 to the 3 joules. This is the work done by the brakes. So I'm just going to write that out here again. Work done by the brakes is negative 17.99 times 10 to the 3 joules, or kilojoules, because it's times 10 to the 3. And remember that this work will be equal to negative the force of the brakes times the distance. So this is really what we want. We have the distance. This is still the 15 meters from before. So let's just quickly rearrange this. We'll get our F brake equals 16.799 times 10 to the 3 joules over the distance. Just write it one more time. Plug in that 15. So if we plug in these numbers, we see we get negative 1.12 times 10 to the 3 newtons. Now this negative, this is telling us really that our force is acting opposite in the direction of motion. So really this is a dot product. And because the force is 180 degrees difference from the displacement is really cos 180, which is negative 1. So we could say the magnitude of the force is actually positive 1.12 times 10 to the 3 newtons. So this is the braking force. So I've just rewritten this up here. Our final answer for part 1, we calculated the normal force at point C. And then for part 2, we calculated how much braking force is required to stop the car safely at part D. And we solved part 2 using the work energy theorem. I'm going to do another video where we solve part 2 using Newton's laws and kinematics only, and we will get the same answer.